With quantum materials, we're trying to take the quantum properties of a material and bring it to the forefront where we can use it and control it. In fact, you already own at least one type of quantum material. If you have a magnet, say holding up a note on your refrigerator, you have a quantum material. In fact, right now, you're listening to my voice through speakers, and your speakers use magnets to convert the electrical signal into a sound that you can hear. Permanent magnets are arguably the first quantum material that humans ever harnessed for technological purposes, when we dug a lodestone out of the ground and then used it to make a compass for navigation. What makes them patently quantum mechanical is that we have a theorem, an actual hardcore theorem in classical physics that says no permanent magnets can exist, ever. So every time you've held a magnet in your hands, you were holding a manifest violation of classical physics that requires quantum physics in order to work. So how do they work? If you take a magnet and heat it up, eventually there's going to be what physicists call a phase transition. Now, if you heat it up enough, eventually the whole thing will melt, which is a phase transition from solid to liquid. You've probably heard of solid, liquid, and gas being different phases of matter. But there are way more phases of matter than just solid, liquid, and gas. In fact, it turns out that electrons inside of materials have their own phases of matter and phase transition. Lots of them, and magnetism is one of them. So if you take a permanent magnet and heat it up, way before the thing melts and becomes a puddle of lava, there will be a well-defined temperature at which the magnetism just suddenly goes away. And then, if you lower the temperature back down, the magnetism comes back. It's a specific temperature at which the properties of the material change dramatically. That's a phase transition. But this phase transition is about what the electrons are doing inside of the material. So how do these electrons work their quantum magic, defy classical physics, and give us permanent magnets? One way is by how they move around inside the material. One way we make magnets on the large scale is not by using a permanent magnet, but it's by making an electromagnet. This is where you take a loop of wire and run a current through it. That electrical current generates a magnetic field. The higher the current, the stronger the magnetic field it produces. Well, electrons inside of a solid, they can form little current loops by going around their atoms, which produces a magnetic field. The other way that electrons contribute to magnetism is much stranger. It has to do with electrons' spin. Now, I'm going to give you an analogy for electron spin, and then I'll tell you which parts of the analogy are wrong. For now, think of the electron as like a charged ball. Now, let that charged ball spin like the Earth rotates on its axis. Well, if that ball of charge spins, then it's also making a current loop. Any current loop produces a magnetic field. It's a little bit like this when the electron is spinning. One problem is that, as far as we can tell, the electron, unlike the ball I used in my analogy, actually has no size. When we go to measure how big an electron is, we can't find a size. It's below our detection threshold. So as far as we know, it's a point particle with zero radius, which wouldn't leave any room for a current loop. And unlike a ball, which can spin fast or slow or even stop spinning, every time we measure how much an electron is spinning, it's always spinning, and it's always spinning by the same amount. It might be spinning clockwise or counterclockwise, but it's always spinning by the exact same amount, no matter which axis we check. It's very strange quantum stuff indeed. So, electrons make these little nanoscale magnets partly by how they move around the atoms inside of a material, and partly by their own intrinsic spin. But what is the specific thing that happens at the magnetic phase transition temperature that changes the material from being not a permanent magnet into a permanent magnet? Above that transition temperature, those little nanoscale magnets are still there, they're just thermally disordered. They're pointing every which way because they're kicked around too much by how all of the atoms are wiggling due to high temperature. But below the transition temperature, all of that wiggling settles down enough so that the nanoscale electronic magnets can line up. And when enough of them line up, their magnetic fields add together, And you get a permanent magnet that you can use to hang a note on your refrigerator or drive the speakers you're using to listen to this right now. Exactly what causes these nanoscale electronic magnets to line up is different in different materials, but it always boils down to three things. Because like charges repel each other, electrons repel each other too. And because in quantum mechanics, particles are waves and waves are particles, each electron has a wave associated with it. The specific shapes that the electron waves take in any particular material, those matter for whether those little magnets want to line up or not. And finally, the Pauli exclusion principle is a patently quantum mechanical rule that says that no two electrons can do the exact same thing at the same time. And all of these quantum effects together, the motion of electrons making little current loops around their atoms, plus their intrinsic spin, combined with the shapes that the electron waves make and the Pauli exclusion principle, all contribute to give us the most common quantum material, one we all use every day, a magnet.